In today's lecture, we will introduce double sideband suppressed carrier, DSB, often written as DSB-SC for suppressed carrier. We'll introduce single sideband and vestigial sideband modulation, all kinds of analog modulation, analog amplitude modulation. So here we are. We're in week 4, but lecture 5 already. We have one more lecture before our class test. Our class test is in week 7. It's on Tuesday, the 10th of March. It should be in your timetables. If it isn't, put it in your timetables. Okay, let me just show you that quickly. That's the date for the class test. So class test, Tuesday, 10th of March, 1 o'clock. So it's not during a timetabled class. So we have a class on Monday, class on Thursday, and the class test is on Tuesday. Okay? So Tuesday, 1 o'clock. If it's in your timetable, you know where to go. If it isn't in your timetable, see the office and make sure it does get on your timetable. If you have a clash with something else, fix it. See the office, fix the clash. Okay? There's 2 class tests worth 15% each. That's your chance to get 30%. Okay? Open book class test, your chance to get full marks. There's no resit. So you take the test, you get the mark. You miss the test, you get a 0. Okay, so do what you can to make sure that doesn't happen. Make sure you know where you're going on Tuesday at 1 o'clock. Now, I might not be there. Okay? Industrial action is happening, so I might not be available. But your test is happening at 1 o'clock on Tuesday, regardless. Okay. Remember last week we spoke about the cat whisker radio or the foxhole radio or the envelope detector. We said it's a very simple circuit that uses a diode and a capacitor to demodulate AM, to use the power within the carrier to trace the envelope and to recover the message. And we said we need careful choice of the components, resistance and capacitance, so that the time constant is sufficiently far away from the 2 extremes of the carrier frequency, the high frequency, and the message frequency, the low frequency FM. We also spoke about power efficiency, and we described how AM is inefficient in terms of power, because more than 2/3, more than 66% of the power is in the carrier. So the amount of useful power in the sidebands is limited. So those were the 3 things we spoke about. We spoke about AM demodulation, we spoke about the spectrum of AM, and we spoke about power efficiency. What we're going to do today is to look at 3 different variations of AM that don't have the same disadvantage. They don't have the same power premium. And next week we'll look at demodulation. Okay? I say next week, what I mean is next lecture. Okay? I can't tell you yet what's happening on Monday, but I can tell you I won't see you on Thursday. Okay? Because it's a 9 a.m. lecture, I'm telling you now, so you don't turn up to a 9 a.m. problem class. Okay? I will try to make available problem sheets and solved questions on YouTube, but there will be no problem class on Thursday. For Monday, turn up and find out. Okay? I'm sorry I can't be more informative than that, but come to the Monday lecture. If I'm here, we'll have a fantastic lecture. If I'm not, you'll have a fantastic break. And we'll have a lecture as soon as we can afterwards on Thursday. Don't worry, we have plenty of time because we're ahead. We have plenty of time. So we will cover everything, and you'll have everything in time for your class test. And you'll have plenty of practice questions too. So don't worry. Remember this? So, for the past 2 weeks, I've been showing you this. And it's an example of what the spectrum of an AM signal might look like. Sometimes our message is a simple sine wave, so we use 2 impulses, and sometimes I use a continuous spectrum like this. So here we have a baseband signal, and it's modulated, so it's shifted up in frequency to our carrier frequency, and we have this carrier component. And we said most of the power is in that carrier component. Now, today we're going to do the same thing. We're going to look at how we can not include the carrier component. So in a way, what we're going to look at today is simpler than AM in terms of modulation. Not as simple in terms of demodulation, but demodulation will be our next lecture. So what we're going to look at today is this same representation but without the carrier. When we finish that, we're going to say, removing the carrier, that saved us some power. What about removing one of the sidebands? That'll save us some bandwidth. And that's what we want to do. We want to save power and save bandwidth. Remember in our first lecture I said, what are the 3 or 4 desirable characteristics of a communication system? We said low power, high data rate, low bandwidth, good quality, low cost, simple components. Okay? So removing the carrier will reduce the power, but removing a sideband will reduce the bandwidth. That's what we're talking about today. So that was our AM. Now we're looking at DSB-SC. Compare that with DSB-LC. LC is for large carrier. Some books will say DSB-FC for full carrier. Or generally we just call it AM. But today we're looking at DSB, which usually refers to DSB suppressed carrier. Suppressed means it isn't there. We've removed it. We've suppressed it. So this is our AM that you're familiar with, where you have a carrier, a message, and you have the DC term. If you multiply that out, and if you remove this, we end up with a simple product where you take your message, M of t, and you multiply it by the carrier. That's all we have. Message, carrier. Message, carrier. Just multiplication. The simplest modulator in the world. You just multiply your message by your carrier. In practice, it's not that simple, but as a block diagram, it's really simple. Carrier times message. And that's the kind of signal we end up with. So if you look at that, it's clear that we can't use an envelope detector for that, because the envelope will be tracing this bit. It won't follow the original message. But that's no problem. We'll be looking at coherent or synchronous modulation scheme next lecture. So this is our block diagram. Simplest block diagram in the world. You have a carrier. You have your message, and they're multiplied. So this is at the modulator. This is prior to transmission. This is at the transmitting side. You have your message from your sensor. Then you have your local high frequency carrier. It's generated by an amplifier, by an oscillator at a certain frequency. That frequency, FC or omega C, that's the frequency that the signal will be transmitted at. That is the carrier frequency. But notice there's no DC term. We're not adding DC. And the reason is because the DC that we used to add, that clamping, that resulted in the spectrum, or the carrier component in the spectrum. This time, we're not doing that. So our spectrum looks much simpler. So same message, very similar spectrum, but what's missing? The carrier component. Because I didn't add DC to the message, there is no carrier component. So we have, is it a less powerful or a more powerful message, signal? Simply removing the carrier makes it less powerful. But if I want to use the same power, in the transmitter, then it becomes much more powerful. How many times more powerful? That's a good question for an exam. Okay, what's different here? The only thing that's different is instead of having a continuous spectrum for my message, I have a discrete spectrum consisting of one component. We call that single tone message. Single tone, where your message is just a sine wave. In real life, who transmits a single sine wave? Nobody. That's the most boring transmission in the world. But remember Fourier theory, that everything can be broken down into sine waves. So if we understand how a sine wave looks and how that's transmitted, everything else is just a combination of sine waves. And mathematically, it's easier to deal with a single tone. So here we have the upper sideband, here we have the lower sideband. Where's the carrier? There's no carrier. Okay, so that's it. That's DSB. That's DSB suppressed carrier. Nothing or not much more to say about that. That's DSB suppressed carrier. So, in DSB, it doesn't send the carrier component. So how much power efficiency do we have? Can we use our little formula, m squared over 2 plus m squared? Can we? No, because there's no modulation index. Why is there no modulation index? Because it's not AM. It's not 100% modulation. 100% modulation, there's still a carrier component. This is DSB, so the power efficiency is 100%. Because all of the signal is useful. So it's 100% efficient in terms of power. However, we still have an upper sideband and a lower sideband. So we're still using twice as much bandwidth as we need. So if we have a 5 kilohertz signal, like that radio station, we'd need 10 kilohertz of bandwidth, which is twice as much as we need. So remember, bandwidth is expensive. Bandwidth is a limited resource. So if we can fit 20 channels into the same frequency, or 40 channels, we'd want to fit 40. So by reducing the bandwidth, we are achieving an advantage in terms of communications, in terms of profitability. So, because both sidebands contain the same information, we can suppress one sideband. So we've already suppressed the carrier, now we want to suppress one sideband and only transmit one sideband. We're not going to go into the mathematics or the electronics of how that happens. We don't have the time for that. It's in any textbook, something called the Hilbert transform. But we'll look at, in the frequency domain, how that looks. So, that's your baseband signal. Your AM signal would be two of those, an upper sideband, a lower sideband, and a carrier. DSB suppressed carrier that we just looked at is the same but without the carrier. Single sideband, or SSB, is where we only transmit one of these, either the lower or the upper sideband. Okay? What does that save us? It saves power, and it saves bandwidth. Well, the saving in bandwidth is obvious. How does it save power? If we send one sideband instead of two, how are we saving power? We don't need to waste power on the other sideband. Or, another way of looking at it is if you want to use the same power, then your sideband will be twice as strong, twice as powerful. So your signal-to-noise ratio will be greater. So there'll be less noise. Disadvantage, it's not as easy to modulate or demodulate. So there's stability in filtering and other issues. So there is a cost to this, but there is an advantage. So the bandwidth, instead of being twice the message bandwidth, 2FM, becomes simply FM. This is the upper sideband. The same would be true for lower sideband. So in SSB, we don't have a carrier. All right, so not only are we only transmitting one sideband, we also don't transmit the carrier. So similarly, the power efficiency is 100%. How do we do this? Well, we take our AM signal. Sorry, I keep changing the shape of the spectrum just to show you that it's arbitrary. It can be any shape. It doesn't matter what the shape of the spectrum is. It can look like a triangle like that. It can look like a triangle like that. It can look like whatever that looks like. Okay? So you'd need some kind of a filter. What kind of filter is that? This one here. Clearly it's blocking. So what you look at, don't look at this bit as something that's being blocked. This is the pass band. Okay, so that's the gain. If you consider that gain to be 1, and here, low frequencies, the gain is 0. So this is a high pass filter. A high pass filter. It's allowing high frequencies to pass. And it's blocking everything from FC to 0. It's blocking all the low frequencies. That's an ideal high pass filter. A non-ideal high pass filter would have a roll-off. So it would leak some of the lower sidebands. So if you want a crisp upper sideband with none of the lower sideband present in the spectrum, if you want full suppression of one of the sideband, you'd need a very high Q filter. A filter with a high order or a high Q factor. You'd want a filter that was as close as possible to ideal. And that comes at a cost. Okay, so that was DSB and SSB. Last thing today, something called vestigial sideband. It's where we have some leakage. But it's not accidental leakage, it's intentional. What we do is we allow some of the lower sideband to pass. We also allow the carrier to pass. Now that doesn't really make sense if you think, well, if you could have blocked one sideband and blocked the carrier, why are you allowing the carrier and allowing some of the sideband to pass? Well, it turns out there are good reasons for this. What we should be comparing it with is comparing it to AM, where you have two sidebands, large bandwidth, and you have a big carrier. Compared to that, vestigial sideband is a little bit better. We can use low-cost demodulator because we have the carrier, low-cost modulator because we don't need a high Q filter. And so we have some of the advantages of AM and some of the advantages of sideband suppression. This is particularly useful or valuable when you have a very wide band message, like in television signals. So in AM radio, the message is maybe 10 kilohertz, but in television, we're talking about 4 or 5 megahertz. So very wide bandwidth. So having two sidebands would be very wasteful. So in practice, we'd use one sideband, a little bit of the second sideband, and we use that second sideband for other information, like audio information. We also have the carrier. Okay. Again, we're not going into more detail than that for vestigial sideband modulation. All right, so this is what a TV spectrum might look like. You have your upper sideband, you have your audio, you have your carrier, then you have your lower sideband with some information, some useful information there. We also, if you notice, there are two carriers. You have your audio carrier and your video carrier, but this is the main carrier that we're interested in. And this is just audio. Okay. This, you've seen this before. Just a summary again of the different frequencies going from LF, MF, HF all the way to terahertz. So you've got satellite and 5G at one end, and you've got the low frequency nautical navigation and AM at the low end. Okay, so quick comparison, then we'll do some questions, and then you're free to go. So AM, we've spoken about it before. It's simple to demodulate. All you need is a diode and a capacitor. You don't even need a power supply. We call that kind of demodulation asynchronous because you don't need a carrier, a local oscillator. It has a wide bandwidth and it's used in commercial AM radio. DSB suppressed carrier is where there's less power available at the transmitter, so it's often used in shorter range applications. So for example, your keyless entry for your car or a garage opener. It's also used in airports for air traffic control. And there's other applications like ham radio, but enough, just think of it as something where power is limited and you need to use a battery that should last a couple of years, 2-3 years, in this little remote fob here. Why is power limited? Because we're not transmitting a carrier, so we can operate on much lower power consumption. SSB is where bandwidth is limited rather than power. So it's good bandwidth utilization. It's used in two-way radios. But demodulation, modulation, a little bit more complex, quality, as a result, sometimes not as good. But it's perfectly fine for voice, for low bandwidth applications, where all you need is 3-4 kilohertz. VSB is for analog television. It's on its way out really now, but still in use. So it's useful to know that we're using a little bit more spectrum than we would on SSB. A little summary for you here. So power efficiency is highest for DSB and SSB because there's no carrier. There is a carrier, remember, for AM, and there is a carrier for VSB. Complexity is lowest with AM and highest with SSB. And these are some of the applications. There are more applications. You're welcome to look that up. A few examples for you. What are we looking at? You need to know that this is single tone message. If I don't tell you this is single tone, you won't be able to answer. But given that this is a single tone message, what kind of modulation is this? Now, could this be SSB? It could be single sideband if I hadn't told you that it was a single tone message. It could be that this is the upper sideband consisting of 2 sine waves. It could be, but I've told you it's single tone. So that means that that is one sideband, that is the other sideband. So we're looking at DSB. Well done. Okay, what are we looking at now?
Can this be DSB? If this were DSB, then these would need to be symmetrical. We would need to be looking at the same amplitude, because we have an upper sideband and a lower sideband that are identical. But they're not identical. So what does that tell us? What kind of modulation scheme is this? It's clearly single sideband.
Are we looking at the upper sideband or the lower sideband? Is this the upper sideband or the lower sideband? We don't know, because you don't know the carrier. And you don't know what the message looks like. But we know that this is probably VSB. Sorry, SSB. What are we looking at now?
There are 6 impulses, so 6 components. But are we looking at 6-component SSB or 3-component DSB, or is it something else?
So, clearly we have an upper sideband and a lower sideband. So it can't be SSB. Is it DSB-LC? No, there's no carrier. There's clearly no carrier term. Now, we have 6 impulses, but there are 3 in the upper sideband, 3 in the lower sideband, so the message must have had 3 components. So it's called a 3-tone message. What's a 3-tone message? It just means 3 sine waves. It just means 3 tones superimposed. So well done. Same signal. What's the carrier frequency? You can't get this one wrong. So the carrier frequency will be halfway between 70 and 80. Another quick question. What's the band pass bandwidth? By band pass bandwidth, I'm talking about the AM bandwidth, the bandwidth as transmitted. So the band pass bandwidth
Is this. The band pass bandwidth is the difference between the highest frequency and the lowest frequency. All right, so you subtract 100, take away 50.
So we're not asking about the message, we're asking about the band pass bandwidth.
This question is now asking about the message bandwidth. Now the message is going to look like that. It's going to be this bit here, shifted to DC. So FC will be shifted to 0. So you subtract FC from everything. So the carrier frequency, remember, was 75. So 100 take away 75 is 25.
So that's your message bandwidth. Remember, message isn't the transmitted signal. So it's not 100 kilohertz. Nothing is 100 kilohertz.
There's no 100 kilohertz here. So whoever you are, that 8%, there's no 100 kilohertz. The bandwidth of the message is 25. The bandwidth of the AM signal, or this DSB signal, is 50. But there's nothing that's 100, because 100 just happens to be this highest frequency.
Remember, for a band pass signal, the bandwidth isn't the highest frequency. It's the difference between the highest frequency and the lowest frequency. Okay, quick solved example.
This is in the problem sheet. Okay, it's solved. And I'll solve it again for you in a YouTube, so I won't waste too much time on this.
But what it's saying is, if we have an SSB transmitter transmitting at 100 kilowatts, and we replace that with a standard AM signal, that means DSB with a large carrier, compare the respective carrier and sideband powers. So I've solved it twice, a long way and a short way. And you can imagine that
power efficiency of 33,
the best we can achieve is 33% in the sidebands. So that's just under 17% in each sideband. and 66% in the carrier. So I've done it one way for you here, and another way, an easier way, using the efficiency here. Okay? I'll leave that for you to read. I'll record a video so you can look at it in your own time. I'm conscious that we only have a couple of minutes. There's one last video I want to share. I was going to share this in the problem class, but I'm not going to see you on Thursday, so I've included it here.
This is often used in ham radio transceivers and things like that to generate single sideband by first starting off with this coming out of the balanced modulator and then using a filter to select one or the other sideband to generate upper sideband or lower sideband modulation. We continue to bring my offset further down.
So what's he showing us here? So on this digital oscilloscope, we're looking at the time domain signals at the top and the spectrum on the bottom. Okay, it's probably a logarithmic scale. It looks like it's not a linear scale, but the bottom half of the scope is a spectrum analyzer. It's a Fourier transform. So when he says FFT, he means fast Fourier transform. Okay. So here we have the carrier component and you have the two sidebands.
We'll come back to the point where the carrier is being raised up again, and once the input signal is fully below the bias point at the input, or the bias point on the other side of the diff pair, now we're back to AM, and we see the familiar AM spectra here again. But just to illustrate this a bit further, I've increased the carrier frequency to 10 megahertz, making it something that's easy for my shortwave receiver here on the bench to pick up. So if we got this set for amplitude modulation, I've got the receiver set to AM, I can actually hear that modulation tone, which I've adjusted to 1 kilohertz. If I adjust that up or down, we can actually hear that.
Now listen to the demodulated signal.
Set to go down to double sideband suppressed carrier. Listen to what happens to the AM signal.
That's distortion.
You can actually hear almost like a second tone, because what's happening is the AM detector is detecting this envelope. We can see the double sideband suppressed carrier basically creates an envelope that includes kind of a second harmonic component to it, and that's why we hear that other tone come in.
Okay, so that was my question. If we try to use an envelope detector to demodulate over-modulated AM, what does it sound like? You just heard that the over-modulation caused there to be an additional higher frequency tone, a second harmonic, double the frequency. Why double the frequency?
Well, if you look at it,
it's half the period, isn't it?
if you look at the signal now, the time between the peaks is halved. So just by looking at it, even without doing the maths, the time between the peaks is now half, and therefore we'll have double the frequency. But if you look at the mathematical representation of a signal after rectification, after full wave rectification, you'll see how the frequencies are doubled and how you have these higher terms. So listen to that and think, what would happen if I were to use an envelope detector, not for over-modulated AM, but for DSB-SC. So if there was no carrier and I still tried to use an envelope detector, what would it sound like? Okay? Because that's also an interesting exam-style question. So in summary, today we've introduced the idea of DSB-SC, and next week or next lecture we will talk about demodulating DSB-SC. We introduced SSB, single sideband. We introduced VSB. We were going to have a problem class on Thursday. That's not happening. Again, we have one more lecture before our class test on Tuesday, the 10th of March. I hope you found that helpful. Do leave me some feedback.